So you've done it. You've spent hours, maybe days, cleaning your data, training a machine learning model. It's finally finished. But here's the big question, the one that really matters. Is it any good? Today, we're going to pull back the curtain on one of the most powerful tools for answering that question, the ROC curve. Here's what we've got on tap. We're going to start with that fundamental problem every data scientist runs into. Then we'll get into what an ROC curve actually is, walk through how to build one, learn how to read its shape, and finally, we'll see how to boil it all down to one single super useful score. All right, let's dive right in. Picture this. You've just finished training your model. You're at that moment of truth.
I mean, it's not enough for it to just run, right? We need to know how well it's actually going to perform out in the wild on new data. We've got to have a way to really measure its predictions.
Now, you're probably familiar with things like a confusion matrix. And don't get me wrong, those are great. But to really truly understand your model, especially a binary classifier, we need something with a bit more nuance. We need a tool that gives us the whole picture of its performance across all kinds of different scenarios. And that tool, my friends, is the ROC curve. It's an awesome way to visualize performance, and it has a pretty cool backstory. Yep, that's right. Before it was a go-to tool in machine learning, this technique was helping radar operators tell the difference between an enemy plane and just, random noise during World War II. Pretty neat, huh? So to see how that applies to our models today, we need to get a handle on three key ideas. First off, the type of model we're talking about. The ROC curve is specifically for a binary classifier. That's just a fancy way of saying it's a model that makes an either-or decision. Like in our source material, the model was trying to predict if a pumpkin was orange or white. That's it. Two options. Second, we've got the decision threshold. The best way to think about this is like a sensitivity dial on your model. Your model spits out a probability, say 70% chance it's a white pumpkin. We need to decide on a cutoff point to make the final call. A lot of the time, it's just set to 0.5. But here's the key. Adjusting that dial and seeing what happens when you do is the entire idea behind the ROC curve. And that brings us to the star of the show, the ROC curve itself. It's simply a graph that shows us the performance of our binary classifier across every single possible setting of that sensitivity dial. It beautifully lays out the trade-offs you're making every time you turn that knob. So how do we actually draw this thing? Well, it's all about plotting two key metrics against each other. These two rates are the heart and soul of our graph. On the y-axis, we have the true positive rate. In our example, that's out of all the pumpkins that were actually white, what percentage did our model get right? Then on the x-axis, we have the false positive rate. Out of all the pumpkins that were actually orange, what percentage did our model mistakenly call white? And this trade-off is everything. Think about it. For medical screening, you want a super high true positive rate, right? You can't miss a real case. But for a spam filter, you'd want a crazy low false positive rate because you absolutely cannot afford to have an important email end up in the junk folder. And building the curve is just a simple recipe. You pick a setting for your sensitivity dial, say a high threshold, like 0.8. You calculate your true and false positive rates for that setting, and you plot that one single point on the graph. Then you just do it again. Try 0.7, 0.6, all the way down. Plot a new point each time, connect the dots, and bam, you've got an ROC curve. Okay, so now we know how it's made, let's get to the fun part, how to actually read it. Because the shape of this curve tells you literally everything you need to know about how good your model is. So, every single ROC curve is locked in by two extreme points. If you crank that threshold dial all the way up to 1.0, your model's going to be super cautious. It'll classify everything as negative. The result? You'll have 0 true positives, but also 0 false positives. That puts you right at the origin, the 0.00. Now, if you swing it all the way to the other extreme, a threshold of 0.0, your model classifies everything as positive. You'll catch all the true positives for sure, but you'll also misclassify all the negatives. That lands you at the top right corner, 1-1. So the goal, the whole point of this, is to get the best of both worlds. We want to jack up our true positive rate, that's the y-axis, while keeping our false positive rate, the x-axis, as low as humanly possible. On the graph, that means we want our curve to get as close as it can to that top left corner. And this gives us a picture of the perfect model. A flawless classifier's ROC curve would just shoot straight up from 0,0 to the 0.01. What does that mean? It means it found 100% of the true positives without making a single false positive mistake. It's perfect. Then it would just go straight across to 1,1. The closer your model's curve hugs that top left corner, the better it is. Simple as that. Now, looking at the shape is great. It gives you a fantastic intuition. But let's be real, sometimes you just need a number, a single score so you can compare one model to another.
How do we take this whole beautiful informative curve that shows us performance across every possible scenario and just boil it down to one number that tells us, at a glance, which model is the winner? Well, the answer is the area under the curve, or just AUC for short. And it's exactly what it sounds like. We're literally measuring the total area underneath our ROC curve. This gives us one single number that summarizes the model's entire performance. What's great about this score is it gives us a really clear scale. That perfect model we talked about, the one that hugs the corner, it has an AUC of 1.0. At the complete other end of the spectrum, a model that's no better than a coin flip will just be a diagonal line, giving it an AUC of 0.5. Most of our real-world models will land somewhere in between. And just to bring it all back home, the pumpkin model from the source material, it was fantastic. Its ROC curve was almost perfect, which meant it got an AUC score really, really close to 1.0. It's a great way to confirm that all that hard work in preparing the data and training the model really paid off. So the big takeaway here is this. The ROC curve and its sidekick, the AUC score, are absolutely essential tools. They give you a much deeper, more complete understanding of how your model is really performing by showing you all the possible trade-offs at a glance. And that leaves us with one final, really practical question for you to think about. The ROC curve shows you the performance at every possible threshold. But for your actual project, you have to pick just one. So you have to ask yourself, is it more costly to have a false positive, like in that spam filter? Or is it worse to have a false negative, like in a medical test? Choosing that perfect spot on the curve for your specific problem, well, that's where the real art and science of machine learning come together.